Everyone, good morning. This is lecture number 11 of ODE. So far, what we are doing is we have been solving differential equations of first order and first degree. So if you haven't watched all the previous videos, go through all the previous videos. This is lecture number 11, right? In this class, I'm going to start solving exact differential equations, right? So I have said in the first class itself that there are many methods to solve a differential equation of first order and degree. Among that, we have completed variable separable method, equation reducible to the form in which the variables are separated, and we have completed homogeneous differential equation. We have completed equation reducible to homogeneous. After that, we have completed linear differential equations, case 1 and case 2. After that, we have solved Bernoulli's equation. Now we are in exact differential equation. Right? Okay. So just go through all the previous videos, right? So first what we will do is we will define what is meant by exact differential of functions, and then we will see one theorem based on exact differentials, and then we will discuss the solutions of exact differential equations. After that we will solve problems based on this, right? First we will define what is meant by exact differential of a function, right? Exact differential. So first we will define what is meant by exact differential of a function of two variables. The definition, the equation mdx plus ndy is equal to 0, where m and n are functions, right? Where m and n are functions of x and y is said to be exact, right? Is said to be exact if this happens, right? Is said to be exact. So we have mdx plus ndy is equal to 0, where m and n are functions of x and y is said to be exact if this happens. If mdx plus ndy, right? mdx plus ndy, if mdx plus ndy, mdx plus ndy is the exact differential, right? Is the exact differential of a function of x and y. That's it. This is the definition of exact differential. The equation mdx plus ndy is equal to 0, where m and n are functions of x and y is said to be exact if mdx plus ndy is the exact differential of a function of x and y. That is mdx plus ndy is the exact differential of the function of x and y. Can be written as d, right? This can be written as du. That's it, right? Here where u is a function of, where u is a function of x and y, right? Or this can also be written as du, right? This u is a function of x and y. So what is du? Right? What is exact differential? We have completed, we have studied in 11th and 12th itself, right? Total differentiation. So what is du? U is a function of x and y. What about d of u? So it will be dou u by dou x into dx plus dou u by dou y into dy. So all these are equivalent, right? So whenever, if you can be able to write mdx plus ndy is equal to du, where u is a function of x and y, it will be exact. Or and we know du is dou u by dou x into dx, dou u by dou y into dy, right? Or this can also be written as, let's do like this, right? Okay. The equation mdx plus ndy is equal to 0, where m and n are functions of x and y is said to be exact if mdx plus ndy is the exact differential of the function of x and y. Is the exact differential of a function of x and y, that is same as du, and we know du is dou u by dou x into dx, dou u by dou y into dy. If you can able to write mdx plus ndy in this pattern, then this mdx plus ndy is equal to 0 is said to be exact, right? But it is not always possible it will be difficult to write mdx plus ndy as a function of this, right? So we're going to introduce one theorem, right? We're going to introduce one very simple theorem that when the equation mdx plus ndy is equal to 0 will be exact without using this result, right? We're going to prove one theorem when the equation mdx plus ndy is equal to 0 will be exact. Very, very important theorem. This theorem is very powerful to check whether the equation is exact or not. So we can check whether exact or not using the definition, but it will take so much of time, right? So rather using this definition, we're going to introduce a theorem that what is the necessary and sufficient condition for an equation mdx plus ndy is equal to 0 to be exact. We're going to introduce one theorem, right? We will prove a theorem when a equation mdx plus ndy is equal to 0, we're going to prove a theorem, right? Okay. Okay. So you can see this can also be written as uh, d of all three are equivalent, right? Du, dou e by dou x dx, dou e by dou y dy, d of u plus integration of f of y dy. This can also be written like this, right? This can also be written like this. Okay. So all three are equivalent, but just understand the definition. Now we'll prove a theorem, right? So theorem, and then you're going to prove this theorem also, right? Very, very important theorem. The theorem, the necessary and sufficient condition. Necessary sufficient condition for the equation mdx plus ndy is equal to 0 to be exact is, right, is given by dou m by dou y is equal to dou n by dou x. That's it. So if this happens, then that equation is exact. You can see what the very huge difference between this and this, right? This is very complicated. But if you have an equation mdx plus ndy is equal to 0, this will be exact if the partial derivative of m with respect to y is same as partial derivative of n with respect to x. That's it, right? So we're going to prove this theorem now. So we have an equation mdx plus ndy is equal to 0. In order to prove that it is exact, is enough to prove dou m by dou y is equal to dou n by dou x. Right? Very, very important theorem. So we'll prove this theorem. This is necessary and sufficient condition. Means that is if and only if theorem. So first what we'll do is we will assume that mdx plus ndy is exact, and then we'll prove this. Right? After that we will assume this and then we'll prove this. Right? So assume right. First what we'll do is we'll assume let the equation mdx plus ndy is equal to 0 be exact, right? I'm assuming this is exact. What we need to prove? We need to prove dou m by dou y is same as dou n by dou x, right? What we need to prove. Okay. So I'm assuming this part, that is I'm assuming this is to be exact, and then I'm going to prove this, right? Okay. So by assumption we have mdx plus ndy is equal to 0 is exact, right? By assuming I'm assuming that this is exact differential. So by definition I can write by definition what is the definition? By definition mdx plus ndy is equal to du. By definition we know, right? So and we know what is du. Du is dou u by dou x into dx plus dou u by dou y into dy, right? You just equate dx and dy, right? Equating the coefficient of dx and dy, equating the coefficient of dx and dy. So equate the coefficient of dx. So we have m to be equal to dou u by dou x, right? Now m to be equal to dou u by dou x and n to be equal to dou u by dou y, right? N to be equal to dou u by dou y. This I'm writing by total differential, exact differential. Both are same, right? So u is a function of x and y. Du will be dou u by dou x dx, dou u by dou y into dy. Okay. So equating the coefficient of dx and dy, we have m to be equal to dou u by dou x and n to be equal to dou u by dou y, right? Okay. Problem is very easy, right? Just understand this theory part. Problem is very easy. Okay. So we have so what about dou m? We need to prove dou m by dou y is same as dou n by dou x, right? So we have found m. So what we'll do is we'll differentiate partial with respect to y. Right? Differentiate partial with respect to y. Differentiate partially respect to y. So we have dou m by dou y, right? Dou m by dou y is equal to dou by dou y of dou u by dou x, right? So dou by dou y of dou u by dou x will be dou square u by dou y dou x, right? And here differentiate partially with respect to x, right? That means dou n by dou x will be dou by dou x of dou u by dou y, so which is dou square u by dou x dou y, right? Now you can see here we have dou square u by dou y dou x and here we have dou square u by dou x dou y. Remember these two are equal. When these two are equal, it is not always equal, but if this u has a continuous second order partial derivative, right? Continuous second order partial derivative, then these two are equal, right? Um, so that means this implies dou m by dou y is equal to dou n by dou x. Now what is u? U is a function of x and y, and if u belongs to C2, right? U belongs to C2, that is this u has to possesses continuous second order partial derivative, right? That is u has continuous second order partial derivative. Then dou square u by dou x dou y. I have already discussed this in calculus, right? Dou square u by dou y dou x. Then these two are equal, right? So therefore, since this u is, I'm assuming that this u has a continuous second order partial derivative. These two are equal, right? Dou y dou x dou y. So therefore, these two are equal. Therefore, dou m by dou x is equal to dou n by dou y. This is called Clairaut's quas theorem, right? This quas theorem in calculus. If u has continuous second order partial derivative, then these two are equal, right? Okay. So we have proved dou m by dou y same as dou n by dou x. Okay. Now we'll prove the converse part, right? I'm assuming that this is exact. I have proved that dou m by dou y is equal to dou n by dou x. And now what we'll do is we'll assume this part and then we'll prove this part, right? So very simple, right? That is, without using the definition of showing whether the equation mdx plus ndy is equal to 0 is exact, we are introducing a theorem, very simple theorem, that this equation is exact, very simple, whenever dou m by dou y is same as dou n by dou x, right? Very powerful theorem. Okay, now we have assumed that this is exact and then we have proved dou m by dou y is same as dou n by dou x, right? How we have proved? My assumption this is exact. Therefore, this mdx plus ndy is du. So you just equate real and imaginary part, find m and n, and to differentiate partially m with respect to y, n with respect to x, so that assuming that this u has continuous second order partial derivative, then these two are equal, right? Okay. Now we will prove that. Now we'll prove the converse part, right? Now we'll prove the converse part. That is what we have defined here, right? Not Prakash. Is there any doubt? The equation m dx plus n dy is equal to 0 is exact if this can be done as in this form, right? So the other way of writing this is, other way of saying that this exact is dou m by dou y is equal to dou n by dou x. Okay. Now we will assume the converse part. Conversely, to assume that dou m by dou y is equal to dou n by dou x, what we need to prove? Now we need to prove that m dx plus n dy is equal to 0 is exact. Right? We need to prove by assuming dou m by dou y is equal to dou m by dou y is same as dou n by dou x. We need to prove that this is exact, right? Okay. Let integration of m dx to be equal to 0 is equal to u. Okay. Integration has been performed. Where integration has been performed treating y as constant. Right? So let integration of m dx to be equal to u. Right? Assume that integration of m dx to be equal to u, where this has to be integrated treating y as constant. Remember, very important. You know, when integrating this integral, when integrating this, you need to treat y as constant, right? Okay. So integrate m dx is equal to, let integration of m dx to be equal to u. Right? Okay. Now, what about what we'll do is we'll differentiate with respect to x partially. So dou u by dou x integration of m dx is equal to dou u by dou x, right? I'm just differentiating partially with respect to x. Okay, partially respect to x, right? So dou u by dou x of m dx is equal to dou u by dou x. This implies m is dou u by dou x, right? M is dou u by dou x, right? So this differential integral will get cancelled. Okay. So we have m to be equal to dou u by dou x. Now we need to, what we need to prove? We need to prove m dx plus n dy is 0 is exact. So let us, we have m to be equal to, let's call this equation to be, right? Very important equation. Let integral of m dx to be equal to u, where integration is performed treating y as constant. So we have, so what is, we have, yeah, we have m to be equal to dou u by dou x, right? M to be equal to dou u by dou x. So what about dou m by dou y is dou by dou y of dou u by dou x, and this will be dou square u by dou y dou x, right? So we have dou m by dou y is equal to dou square u by dou y dou x, right? And by assumption, we know that what we can do is, okay, now this is same as dou square u by dou x dou y, provided this u belongs to C2, right? Provided this u belongs to C2, right? That is, this u has continuous second order partial derivative. And we know by assumption that this dou m by dou y is same as dou n by dou x, right? So by assumption, we know dou m by dou y is same as dou n by dou x. Therefore, I can interchange this term and I'm replacing dou m by dou y to be equal to dou n by dou x, right? So we have dou n by dou x is equal to dou square u by dou x dou y. Now integrate with respect to x. Now um, integrate, let's call this equation to be equal to 2. Let's call this equation to be equal to 3. Right? Okay. Now integrate with respect to x, treating y as constant. Right? Treating y as constant. So you need to integrate with respect to x, right? Okay. That means integration of dou n by dou x, integration of dou square u by dou x dou y dx, right? Treating y as constant. Remember, this is very important. That means this will be n. So n is equal to dou u by dou y plus a function of y. This is what you will have whenever you are integrating this function with respect to x. Right? Very simple. You just take a function of two variable. You just find this and integrate with respect to dx. This is what you will have. This is what you will have. Very simple, right? Let us take u to be equal to x square plus 2xy square, right? Take this function. Now you just find this value of this integral, right? Find dou square u by dou x dou y, and then you integrate with respect to x. What you will have is you will have dou u by dou y plus a function of y. Very simple, right? You can easily check what you can easily check it out. Okay, that means dou u by dou y plus a function of y. Let us say it is equal to f of y. Right? Let us say this f of y. Call this as equation number 4. Right? So from 2 and 4, from 2 and 4, okay. Now, what about m dx plus n dy? Now, what is m? M is dou u by dou x, right? M is dou u by dou x into dx. And what is n? Dou u by dou y plus f of y into dy, right? From 2 and 4. From 2 and 4. What is our aim? Our aim is to prove that this is exact. That is m dx plus n dy is equal to 0 is exact, right? Okay. So we have found m is dou u by dou x, and we have found n, which is dou u by dou y plus f of y. Right? Very simple. So I'm assuming that integration of m dx is equal to 0, where integration has been performed, treating y as constant. Now differentiate partially with respect to x, right? So you will have m to be equal to dou u by dou x, and find dou m by dou y, and interchange this, and you can replace dou m by dou y to be equal to dou n by dou x by assumption, and find n from here and substitute back in, right? Okay. So this will be equal to this. I can write this as dou u by dou x into dx. You just bring this dy inside, right? Dou u by dou y into dy plus f of y dy, right? Plus f of y dy. Now this is nothing but du, right? This is nothing but du, because du is, we know, right? Dou u by dou x into dx, dou u by dou y into dy plus f of y into dy. This can be done as d of, right? D of u plus integration of f of y dy, right? Both are same, right? If I bring d inside, it will be du, and this differential integral will get cancelled, which is exact, right? This is the definition of exact, right? M dx plus n dy is equal to d of u plus integration of f of y dy, right? So that means it is exact. This exact differential, hence, so we have proved that this is exact, right? So very simple part. So just understand the proof, very easy proof. Now the main part is, whenever you need to prove whether the equation m dx plus n dy is equal to 0 is exact, what we need to prove? We need to prove dou m by dou y is equal to dou n by dou x. If this happens, then this will be exact equation, right? Okay. Now we're going to introduce. Now we're going to see about what is the solution of exact differential equation, right? So when will be exact differential equation? Whenever m dx plus m dy is equal to 0 is said to be exact if this happens. Now what is solution? That is what we're going to discuss now, right? See, This is theory part. Very simple. Problems are very simple. We'll do the problem, then you will come to know. Solution of exact differential equation. Solution of exact differential equation. Right? If the equation, mdx plus ndy is equal to 0 is exact, then we know that mdx plus ndy is equal to du, right? Equal to du, or this can be written as d of u plus integration of f of y dy, right? This we know, right? Both are same, right? By definition, all three are same. So mdx plus ndy is equal to 0 is exact if mdx plus ndy is equal to d of u plus f of y dy. Um, Now we need to find the solution of mdx plus ndy is equal to 0, right? Okay. Now, therefore, mdx plus ndy is equal to 0. That means what? So we can write mdx plus ndy to be equal to d of u plus integration of f of y dy is equal to 0. We are finding the solution of this equation, right? We are finding the solution of this equation. And we know this equation is exact. Now that means what? Derivative of this is 0. That means what? This is constant, right? Derivative of something is 0 means that has to be constant. This implies u plus integration of f of y dy is equal to some constant, right? It is equal to some constant. So we know that what is u? By assumption, we know that from 1, we know that u is integration of mdx, right? So that means from 1, let's call this as equation number 5. From 1, we know that u is integration of mdx, where this integration is performed treating y as constant, right? Integration is performed treating y as constant. I can replace this u to be equal to integration of mdx treating y as constant, implies integration of, so that means this 5 will become integration of mdx. This integration is performed treating y as constant. This is what you need, right? So if this integration is performed treating y as constant plus integration of f of y dy, and we know this f of y dy is what? F of y, from 4, f of y is n minus dou u by dou y, right? Yes. So we have f of y, right? Yes. So from 4, what is f of y? You can see f of y is n minus dou u by dou y, right? N minus dou u by dou y is f of y into dy. This is from 4. Right? Now remember, c equal to c. So we have integration of mdx. This integration is performed treating y as constant plus integration of n minus dou u by dou y will turns out to be terms in n not containing x. Not containing x into dy is equal to c is the required solution. That's it. Right? N minus dou u by dou y will turn out to be terms in n not containing x. Right? Terms in n not containing x. I'll do the problem, then it will be easy for you. Right? Therefore, the solution is given by integration of mdx plus integration of terms in n not containing x into dy is equal to some constant. Right? Here this integration is performed treating y as constant. This is the solution of exact differential equations, right? Solution of exact differential equation, right? Very, very simple. In exam point of view, you just have to understand this part. That's it, right? In exam point of view, you just have to understand. You just have to by heart this. That's it. Solution of exact differential equation is integration of mdx. This integration is performed treating y as constant plus integration of terms in n not containing x into dy is equal to c. Right? So we'll do some problem. It will be very easy for you. So far, what we did is we introduced the equation mdx plus ndy is equal to 0 is exact. If this happens, but it is in order to prove it is exact, it is sufficient and necessary condition is dou m by dou y is equal to dou n by dou x. If the equation is exact, the solution is given by integration of mdx plus integration of terms in n not containing x dy is equal to c. Right? Okay. N minus dou by dou y turns out to be this part, right? You just take a function and then you will check it out, right? Okay. Okay, so we'll do problems, right? Okay. Is there any doubt up to now? Solve solve power y. So e power y plus 1 cos x dx plus e power y sin x dy is equal to 0, right? Okay. Now comparing with mdx plus ndy is equal to 0. So comparing with mdx plus ndy to be equal to 0. What is m? M is e power y plus 1 into cos x. And what is n? N is e power y sin x, right? N is e power y sin x. Okay. Now, if it is exact, then I know solution, right? If it is exact, I know the solution. This is the solution, right? Now we will check whether. Now, what is dou m by dou y? Right? So, what is dou m by dou y? Differentiate partially with respect to y, right? So, you know how to differentiate partially, right? So, what is dou m by dou y? So, you just have to write this e power y cos x plus cos x. So, if we differentiate with respect to y, that means cos x will be constant. So, e power y cos x. So, cos x is constant. So, whenever you are treating with partially means you need to treat other variables as constant. That is the main difference, right? Whenever you are differentiating partially with respect to some variable means you treat other variables to be constant, right? So here cos x is constant, derivative of e power y is e power y, and the derivative of cos x is 0, right? Because we are differentiating partially with respect to y, but we have cos x here, so this will be 0. So we have e power y cos x. So what about dou n by dou x with respect to x? So e power y is constant, derivative of sin x is cos x. So we have dou m by dou y is equal to dou n by dou x, right? Dou n by dou x. This implies the equation mdx plus ndy is equal to 0 is exact differential equation. If it is exact differential equation, what is the solution? We know solution, right? Solution is given by integration of mdx integration of m dx plus integration of terms in n not containing x, into dy is equal to constant. This you have to integrate treating y as constant. This is a solution, right? Solution is given by this. This is solution after proving that the given equation is exact, right? Solution is this solution, right? Okay. Now very simple, right? You need to integrate. Now integration of what is m? Integration of what is m? M is e power y cos x, e power y plus 1 cos x. So e power y plus 1 cos x. This has to be integrated treating y as constant into dx plus terms in n not containing x. So we have only one term and this term containing x. Containing x means some functions of x, right? So that means there is no term. This will be 0 because there is n has only one term which contains x, right? Which contains x. We can see we have sin x. That means there is no term in n that does not contain x. This will be 0. So we need to integrate this treating y as constant. So therefore, integration of e power y cos x plus integration of cos x dx is equal to c. Remember, this has to be performed treating y as constant. That means if you take this e power y outside, because y terms are constants. Y terms are constant. For integration of cos x, it will be sin x plus integration of cos x is again sin x. C equal to c. If I take this sin x outside, so e power y plus 1 sin x is equal to c is a required solution. Very simple problem. It seems to be slightly something what confusing, but very simple, right? You just prove it is exact. So whenever you have m dx plus n dy is equal to 0, you prove it is exact by showing dou m by dou y is equal to dou n by dou x. If it is exact, the solution is integration of you need to treat this as constant, right? Integrate with respect to dx, treating y as constant. So take e power y outside. Very simple answer, right? So second problem. Is there any doubt? So second problem. So solve a square minus 2xy minus y square dx minus x plus y whole square dy is equal to 0, right? Okay. We have m to be equal to a square minus 2xy minus y square, m to be equal to minus of x plus y whole square, right? M dx plus n dy. Okay. So this is minus of x square plus 2xy plus y square, right? Yes, okay. So we have n to be equal to minus of, so we take this minus inside. Okay. Now, what about dou m by dou y with respect to y? So this will be minus 2x minus 2y, right? This will be 0. Minus 2x is constant. Derivative of y is 1. This will be 2y. What about dou n by dou x with respect to x? So it will be 2x plus 2y. So this means minus 2x minus 2y. So we have dou m by dou y is equal to dou n by dou x. This implies it is exact, right? is exact. If it is exact, we know that the solution is given by solution is integration of m dx. This integration is performed treating y as constant plus integration of terms in n not containing x into dy is equal to c. Right? Means integration of m dx. So what is m? It is a square minus 2xy minus y square dx plus integration of terms in n not containing x. So you can see we am audible. Okay, so we have n to be equal to, so we have n to be equal to minus x square minus 2xy minus y square. This contains x, this contains x. So we have this terms in n not containing x. So we have three terms in n, but two terms contain x. So we will have minus y square dy is equal to c. Right? So this has to be performed treating y as constant. So integrate this. So a square will be a square x minus 2y is constant. So integration of x dx is x square by 2. Now remember this has to be integrated treating y as constant. Right? So this means y square integration of dx is x. Right? Very simple. Now this will be minus y cube by 3 is equal to c. That's it. Right? This is the required solution. So a square x minus x square y minus xy square minus y cube by 3 is equal to constant is the required solution. Right? So to find the terms in n not containing x, you just write down the terms of n. There are three terms here. Strike out all the terms that has x. So you'll have only one term that does not contain x, which is the term is minus y square. Now this has to be interpreting y as constant. Right? We'll do one more problem. So we'll do one more problem and then we'll wind up. Dx square plus 6xy square dx plus 6x square y plus 4y cube dy is equal to 0. Right? We have m to be equal to 3x square plus 6y square x, right? Now what about dou m by dou y will be 0 plus 6x is constant. Derivative of y square is 2y. So we will have this to be 12xy and we have n to be equal to 6x square y plus 4y cube. What about dou n by dou x? Again 6y is constant, derivative of x. We will have 12xy. So we have dou m by dou y is equal to dou n by dou x, which is exact. So if m dx plus n dy is equal to 0 is exact, the solution is given by integration of m dx plus integration of terms in n not containing x into dy is equal to c, right? This has to be integrated treating y as constant. So integration of what is m is 3x square plus 6xy square dx plus terms in n not containing x. Terms in n not containing x. So we have n to be equal to 6x square y plus 4y cube. So we have two terms in n. This contains x. This does not contain x. So that means we will have 4y cube, right? This 4y cube dy is equal to c. This has to be performed treating y as constant. So 3 into derivation, sorry, integration of x square is x cube by 3 and the 6y square is constant. The integration of x dx is x square by 2 will be 4 into y power 4 by 4 is equal to x cube plus 3x square y square plus y power 4 is equal to c is the required solution. Right? You just have to prove it is exact by showing dou m by dou x dou m by dou y is equal to dou n by dou x. If it is exact, we know the solution is integration of m dx plus integration of terms in n not containing x. Right? Very simple. Next class, we will solve more problems based on exact differential equations. So we'll continue in the next class, right? So if you have any doubt, you can ask. Okay, thank you.